So imagine trying to build like a massive continent-spanning train network.
Okay, a train network.
Yeah, and you have all the steel, you have the engineers. The funding is totally secured.
Right. Sounds like a good start.
But there is one catastrophic problem. Every single country you cross into uses a completely different sized train track.
Oh, man. Yeah, that's a logistics nightmare.
Exactly. Because without standardizing that track width, your multi-million-dollar high-speed trains are just, well, they're going to crash.
Or at best, they just stop dead at the border, right? And you have to, like, manually unload every single piece of cargo.
Exactly. And that is exactly what happens in the digital world without spatial data standards.
It really is. It's the exact same concept, just with data instead of steel.
Right. And if you are listening to this deep dive right now, you are likely gearing up to conquer Section 208 of the GISP exam.
The dreaded Section 208.
The dreaded one. Yeah. Because you already know that staring down the required knowledge for this section, all the ISO codes, the FGDC mandates, the OGC web services, it feels less like studying and more like drowning in alphabet soup.
It is incredibly dense material. I mean, it's just acronym after acronym.
It really is.
But, you know, those acronyms represent the invisible infrastructure that makes every modern geographic information system actually function.
Right.
So our mission today is to kind of act as your personal decoders. We want to move past the rote memorization of all those acronyms.
Because just memorizing them won't help you understand how they actually work under the hood.
Exactly. When you understand the mechanisms, like why a specific XML schema was created in the first place, or how a web server handles a tile request, those abstract exam concepts transform into sticky, memorable tools.
Tools you can actually use on the job. So we need to know who is writing them.
Let's meet the rule makers.
Yeah, let's look at the first of the big three organizations you really need to know for the GISP exam. Starting on U.S. soil, the Federal Geographic Data Committee, or the FGDC.
The FGDC. They are the lead policymaking entity in the United States government for geospatial data.
And they're chaired by the Department of the Interior.
Right. They are. Their primary mission is overseeing the National Spatial Data Infrastructure, or the NSDI.
The NSDI,
Yeah.
which is the framework that allows the public and private sectors to share spatial data seamlessly.
Exactly. Now, for the exam, you need to understand where their authority actually comes from.
Right. They didn't just give it to themselves.
No, it is backed by the Geospatial Data Act of 2018 and, critically, by Office of Management and Budget, or OMB, circulars, specifically A16 and A119.
Okay, let's break down what an OMB circular actually does, because honestly, it sounds like bureaucratic trivia.
It really does.
But it's the engine driving all of this. The Office of Management and Budget controls the purse strings for the federal government.
The money.
Right. So when Circular A16 directs the coordination of geographic information, it's basically a mandate telling federal agencies, if you want funding, you have to share your data using our rules.
That financial leverage is exactly how standards become widely adopted. And under that mandate, the FGDC created two massive legacy standards.
Okay, what's the first one?
The first handles the documentation side. It's the CSDGM, or the content standard for Digital Geospatial Metadata.
That is a mouthful.
It is. Historically, this required federal agencies to document all new geospatial data with specific fields.
Like what kind of fields?
Things like the title, abstract, date, geographic extent, and the projection information.
Okay, so that's the documentation piece.
Yes.
And on the accuracy side, the FGDC created the NSSDA, right? The National Standard for Spatial Data Accuracy.
Yes, the NSSDA. And the exam materials get incredibly specific about the testing metrics for this one.
They really do. They state that an accuracy assessment requires 20 to 30 evenly distributed test points across your map.
Right.
But it goes further. Each quadrant of your test area has to contain at least 20% of those points. Why dictate the geometry of the test itself?
It's all about preventing clustering bias.
Clustering bias.
Yeah. If you are assessing the accuracy of, say, a county-wide map, and you only test 20 points in the highly developed downtown area because it's easier to access.
The survey crews can just drive there.
Exactly. Then you have no idea if the rural areas on that map are actually accurate.
Right.
So forcing a 20% minimum in every quadrant guarantees a statistically valid spatial distribution.
That makes total sense. But there's another crucial detail about the NSSDA that trips up test takers. It only assesses point accuracy.
Yes.
I saw that in the notes and it totally threw me off. If I'm mapping a winding highway or like a complex river network, The NSSDA doesn't evaluate the continuous line.
It does not. Statistically, you cannot easily measure the accuracy at an infinite continuous line.
Oh, I guess that's true.
So the standard requires you to extract specific, well-defined points along that linear feature,
Like what?
like the sharp intersection of two roads, and you compare those discrete points against an independent source of higher accuracy, like a real-world ground survey.
Okay, so the FGDC builds these incredibly robust rules for federal agencies. Does a private sector GIS analyst, like someone working at a commercial real estate firm, actually need to care about the CSDGM or the NSSDA?
Since they don't answer to the federal government.
Right.
Legally, no, but practically, yes.
Why is that?
Because if that real estate firm ever wants to overlay their private property data with FEMA flood zones or USGS elevation models, using the same metadata framework saves hundreds of hours of data cleaning.
Oh, right, because you want your train on their track.
Exactly. However, the everyday application of the FGDC's unique standards is currently undergoing a massive plot twist.
A plot twist.
Yeah, and it ties back to that other budget document we mentioned earlier, OMB Circular A119.
Right, A119, because Circular A119 directs federal agencies to use voluntary consensus standards rather than inventing their own.
Correct.
Basically, the government realized it was wasting money building its own isolated train tracks.
Exactly. Data does not stop at the U.S. border. Climate models, ocean currents, global supply chains, they all require international collaboration.
So because of A119, the FGDC is actively retiring its proprietary standards like the CSDGM.
Yes, and they're replacing them with global standards.
Which brings us to the second giant organization on our list, ISO, the International Organization for Standardization.
ISO.
They're the global diplomats of data.
That's a great way to describe them. In the geospatial realm, ISO standards are maintained by a dedicated group known as ISO Technical Committee 211.
TC 211.
Right. And before we dive into their specific codes, there is a fundamental difference between ISO and the other groups we are discussing today, and it is a classic exam question.
Ooh, okay. What is it?
ISO charges fees for their standards.
Wow. That is a brilliant trap for a multiple-choice question. You would assume an international standard designed for global interoperability would be completely open access.
Right, you'd think so.
But no, you actually have to purchase the official documentation. And the documents the exam focuses on are part of the ISO 19100 series.
Specifically the metadata suite.
Right. We have a lot of numbers to decode here.
We do. Let's start with the anchor of the entire suite, ISO 19115.
Sometimes written as 19151.
Exactly. This is the core metadata standard that is actively replacing the FGDC's older models.
Got it.
It defines the absolute minimum vocabulary required to describe geospatial data. It enforces mandatory fields like the dataset title, the creation date, the language, and the topic category.
Okay, so that's the core. Then you have extensions. The materials really highlight ISO 19115 too.
The -2 extension specifically handles metadata for imagery, gridded data, and data collected from instruments.
Like a remote weather station.
Yes, exactly. It adds fields to describe the sensor type, the angle of the satellite, or the atmospheric conditions during data capture.
But the standard that always seems paired with 19115 is ISO 19139.
Yes, very important distinction.
And understanding the difference between these two is critical for the exam. From what I gather, ISO 19115 tells you what information needs to be captured, but ISO 19139 dictates how the computer actually reads it.
You are describing the exact difference between a conceptual model and an implementation schema.
Okay.
ISO 19139 provides the XML schema, the extensible markup language format, for the 19115 standard.
Let me try an analogy here to cement this for the listener.
Go for it.
Think of ISO 19115 like the blueprint or the required vocabulary that says, hey, you must provide a publication date.
Right.
But human beings write dates differently.
Mm.
Month first, day first, spelled out, abbreviated.
It's a mess.
And a computer gets completely confused by that.
Yeah.
So ISO 19139 is the grammar. It dictates the exact XML tags, forcing you to bracket the date in code so a machine can parse it instantly without error.
That analogy perfectly captures the mechanism. ISO 19115 is for the human brain designing the database. ISO 19139 is the strict code structure the server actually parses.
That makes it so much clearer.
And what makes ISO brilliant is this modular suite approach.
Right, you don't have to adopt everything.
Exactly. You don't have to adopt a 1,000-page standard if you don't need it. If you are just mapping basic points, you use 19115 and the 19139 XML.
But if you add satellite imagery, you pull in 19115 too.
Right. It keeps the data architecture as lightweight as possible.
Okay, let's round out the rest of the ISO flashcard numbers really quick. ISO 19157 handles data quality standards.
Establishing the framework for measuring positional and thematic accuracy.
Then ISO 19111 governs spatial referencing by coordinates.
Ensuring the complex math behind map projections translates globally.
And ISO 19125 defines simple feature standards.
Which are the fundamental geometric storage models, points, lines, and polygons.
Awesome. Knowing those numbers is basically non-negotiable for Section 208.
Absolutely.
But so ISO handles the heavy formal metadata framework, but they don't dictate how a web map actually loads dynamically onto your smartphone.
No, they don't do that at all.
Which is the perfect transition to the third pillar of our deep dive, the OGC, or the Open Geospatial Consortium.
Right.
If ISO is the formal global diplomat, the OGC is the agile engineer actually building the internet.
I like that. The OGC is a neutral international forum made up of hundreds of companies, government agencies, and universities.
And their overriding mission is to make location data fair.
FAIR, an acronym standing for findable, accessible, interoperable, and reusable.
And right off the bat, contrasting directly with ISO, OGC standards are completely free of charge.
Yes. A critical distinction for the exam. The OGC is responsible for many of the file-based standards you likely use daily.
Like what?
They standardize KML and KMZ, which Google Earth brought into the mainstream.
Okay.
They manage the GeoPackage format, GeoTIFFs for spatially referenced imagery, and LAS files for point cloud LiDAR data.
And they also created GML, right? The geography markup language.
Exactly, which is an XML grammar specifically designed to express geographical features.
But the real meat of the OGC, and where test takers usually start sweating, is their suite of web-based standards, the wall of W acronyms.
Oh, yeah. WMS, WFS, WCS, WMTS, WPS.
It's too much. These web services allow a user to access spatial data over the internet, as if it were sitting on their local hard drive. But if you just try to memorize the acronyms, they all blur together.
They really do.
We need to explain the mechanics of what these services actually do when you ping a server.
Okay, let's build a map from scratch over the web to differentiate them.
Let's do it.
You open a browser and you want a visual reference map. Use a WMS, a web map service.
Go WMS.
The server takes its raw data, renders it into a flat image like a JPEG or PNG, and sends you the picture.
So it's just a picture.
Right. It is fast, but it is static. You can look at the property boundaries, but you cannot click on a parcel and edit its shape.
Okay, and the defining server commands here are get capabilities, which asks the server what maps are available, and get map, which requests the actual image. Okay, but say I'm a city planner. A picture isn't enough. I need to select a specific zoning parcel, view its attributes, and actually reshape the polygon. A WMS won't let me do that.
No, it won't. For that, you need a WFS, a web feature service.
Web feature service.
Instead of sending a flat picture, the server sends the actual discrete vector geometry, the points, lines, and polygons, along with their attribute tables.
So I get the real data.
Yes.
No.
This requires significantly more bandwidth, but it allows the client to create, delete, update, and query specific features dynamically.
So WMS is the picture. WFS gives me the interactive vector shapes.
You got it.
But what if I'm a hydrologist and I need to analyze a digital elevation model? Vectors won't help me there.
Nope. Then you call on a WCS, a web coverage service.
Web coverage service.
This standard delivers multidimensional coverages in a raw raster format. We aren't talking about a JPEG picture of elevation.
Right.
We are talking about the actual grid of data where every single pixel contains a raw mathematical value. WCS is designed for heavy analysis of space-time phenomena, like temperature grids or soil saturation models.
Okay, this progression makes total sense. We go from a simple picture with WMS to editable vectors with WFS to raw analytical rasters with WCS.
Exactly.
But there's another web service that seems redundant at first glance. WMTS, the Web Map Tile Service.
Ah, yes.
If we already have WMS for pictures, why do we need tiles?
It comes down to server mechanics and speed.
Okay.
If millions of users are panning and zooming around a WMS web map simultaneously, the server has to custom render a brand new massive image for every slight movement.
Oh, it would crash instantly.
It would burst into flames. A WMTS solves this by pre-rendering the map at various zoom levels and chopping it up into millions of tiny independent square image tiles.
So when I drag a map on my phone and I see those little blank gray squares rapidly filling in with map graphics, That is the WMTS in action.
That's it.
My phone is only asking the server for the specific small squares I moved into, rather than requesting a completely new map of the entire city.
Exactly. It uses a caching mechanism to drastically reduce processing power and bandwidth.
Brilliant.
And finally, there is the WPS, the Web Processing Service.
Web processing service.
This standardizes how you invoke complex geospatial processing rules over the web.
Give me a real-world use case for WPS.
Suppose you are working on a low-power laptop out in the field, and you need to run a computationally massive Vust analysis.
Like calculating everything visible from 100 different mountain peaks.
Right. Your laptop would melt trying to process that locally.
Totally.
Using WPS, you send the data and the parameters to a remote supercomputer. The server does the heavy mathematical lifting and simply sends you back the finished result.
Oh, that's amazing.
Its key commands are get capabilities, describe process to understand the inputs required, and execute to run the math.
Okay, so WMS for the picture, WFS for the vectors, WCS for the raw rasters, WMTS for the fast pre-chopped tiles, and WPS to make the server do the heavy math.
You've got it.
Tying the acronym to the actual computational mechanism makes them impossible to forget.
And that covers in the modern foundation. We have the FGDC setting U.S. policy, ISO handling global metadata structures, and the OGC building the Internet interoperability protocols.
Big three.
But to ensure you are fully prepared for the exam, there is one final section of our outline to cover.
Right.
We need to discuss a few legacy organizations and highly specific accuracy metrics that still routinely appear on test questions.
Let's start with ANSI and the SDTS. ANSI is the American National Standards Institute. What is their role in all of this?
ANSI is essentially the official United States representative body within the international ISO framework.
Okay.
And decades ago, ANSI developed something called the SDTS, the Spatial Data Transfer Standard. It was a robust method for archiving and transferring spatial data across different computer platforms.
But the sources indicate that the SDTS is essentially a dead standard now, heavily phased out in favor of the OGC's Geography Markup Language, or GML.
It is.
So why do we still need to study it?
Because the accuracy testing methodologies defined within the SDTS laid the groundwork for how we think about quality control today. And those specific rules still pop up on certification exams.
Gotcha.
For instance, the SDTS established that any raster data being transferred must meet a 95% accuracy threshold.
And it has a notorious rule regarding test points, right?
Yes, it does. For positional accuracy tests, the SDTS requires you to test a minimum of 20 checkpoints against an independent source of higher accuracy.
Could be 20 points.
And out of those 20 points, only one single point is allowed to fail the test.
Only 1 point can fail out of 20. That is a 95% pass rate on discrete points.
It's very strict.
Think about the pressure that puts on a field crew conducting a survey. You have zero room for a sloppy GPS reading or a rushed measurement.
Absolutely zero room.
Speaking of intense accuracy thresholds, we also need to mention the historical map accuracy standards set by the Federal Bureau of the Budget.
Yes.
The numbers here sound abstract, but the real-world implications are massive.
These are the legacy national map accuracy standards. They dictate that for maps with a publication scale larger than 1 to 20,000, 90% of the tested points must fall within 1/30th of an inch of their true ground position.
1/30th of an inch on the printed page. That sounds like the width of a pencil line.
It basically is.
But let's actually do the math to understand why this matters. A scale of 1 to 20,000 means 1 inch on the map equals 20,000 inches in the real world.
Right.
If you divide 20,000 by 30, you get about 666 inches, which is roughly 55 feet. So 1/30th of an inch on that map translates to 55 feet of wiggle room on the ground.
When you convert the fraction to actual footage, you instantly see the stakes. If a utility company is relying on a municipal map to find a buried water main, a 55-foot margin of error is massive.
You could tear up an entire city block before you find the pipe.
Exactly. This is why the Bureau of the Budget mandated these strict tolerances.
Makes sense.
Furthermore, for maps smaller than 1 to 20,000 scale, 90% of points must be within 1/50th of an inch.
Even tighter.
And for elevation data, 90% of all tested points must fall within 1/2 of a contour interval.
These legacy standards highlight a crucial strategy for the exam: The test frequently challenges your ability to distinguish the primary mission of an organization from its secondary activities.
Very true.
There is a sample question in the study materials that asks you to select the most accurate description of the FGDC's role.
It is a brilliant example of a distractor question.
How so?
The options usually include technically true statements like, the FGDC utilizes ISO standards for metadata. While that is a true fact today, it is not their core identity.
Right.
The correct answer focuses on their fundamental mandate. The FGDC is the lead entity in the U.S. government for developing geospatial policies and coordinating the national spatial data infrastructure.
You have to focus on the organization's origin story, not just a trivia fact about their current operations.
Exactly.
If we zoom out and look at everything we've decoded today, it really forms a cohesive cheat sheet for Section 208.
It does. When you encounter the FGDC, your mind should immediately anchor to the U.S. Department of the Interior, federal policy, the NSDI, and legacy standards like the CSDGM and NSSDA.
When a question brings up ISO, you immediately pivot to international global coordination, paid standards, and the crucial 19100 series.
Specifically knowing that 19115 is the conceptual blueprint and 19139 is the XML grammar that makes it readable by a machine.
And when you see the OGC, you look for answers involving internet interoperability, the fair data principles, completely free access, and the computational mechanisms behind all those WWeb services.
WMS for images, WFS for vectors, WCS for rasters.
We started this deep dive talking about how standards prevent the data trains from crashing at the border. You are now equipped not just with the acronyms, but an understanding of the tracks themselves.
You're ready to build the network.
But before we wrap up, diving into all these legacy standards, from the Bureau of the Budget to the phase-out SDTS, brought up a thought that I can't quite shake.
Oh, what is the concern?
Well, we spend so much time talking about interoperability in the present, but standards are constantly evolving and replacing one another.
That's true.
The FGDC's CSDGM is actively being overridden by ISO 19115. The SDTS is being abandoned for OGC's geography markup language.
Right.
It is a constant, relentless churn of technological progress. But what happens to the petabytes of perfectly documented historical data trapped inside those dead standard formats?
Oh, wow. You were talking about decades of environmental baseline studies, historical property boundaries, and legacy infrastructure maps.
All perfectly formatted for software that might not exist in 20 years.
Exactly.
As we keep changing the track gauge for our data trains to accommodate the future, will the GIS professionals of tomorrow find themselves spending just as much time acting as digital archaeologists struggling to translate and unearth dead formats as they do analyzing new data?
That's a fascinating point.
We spend so much energy ensuring we can communicate with other agencies today. We might be losing the ability to communicate with our own past.
It is the great paradox of standardizing technology. The solution that solves today's interoperability crisis often becomes tomorrow's legacy barrier. It is a profound challenge for the next generation of analysts.
It is definitely something to mull over while you're memorizing those ISO numbers. Just remember, whether you are trying to decode a 19th century paper maps projection or pinging a 21st century web processing service, the underlying mission is exactly the same: making sure the data is trustworthy and making sure the train stays on the tracks. Good luck on the exam. You've got this.